Hi everybody. Today's video is going to talk about uniform circular motion. This is our first introduction to uniform circular motion, so we're going to get to some basics. I have some things written down up here. I'm going to take a second to read through here and then kind of explain what some of this means. So uniform circular motion refers to any object moving in a circular path with a constant uniform speed. While the speed does not change, the direction the objects move is constantly changing. This means that the velocity is not constant. As the velocity is constantly changing, a net balance force is needed to cause circular motion. This net force is called the centripetal force and causes centripetal acceleration. The term centripetal means center seeking. The net force and therefore acceleration will be directed towards the center of the circular motion for all objects moving with a uniform circular motion. Okay, what does all that mean? Well, first of all, remember velocity is a vector. And so if we have constant velocity, that means it would be constant, the same vector all the time, and that means going in the same direction. So constant velocity would mean a vector moving in the same direction, but that's not what's happening with circular motion. With circular motion, we're going in a circle. And so the velocity is always changing direction. And so it is not constant velocity. If it's not constant velocity, then by definition, it must be acceleration. Things in motion tend to stay in motion in a straight line. So there must be a force making it go in a circle, and that's the centripetal force. So if you have a ball and you roll it down the hall or down the driveway or down the street or whatever, down the bowling alley, it is going to go in a straight line unless something makes it move in a different manner. And so something going in a circle, something has to be making it go in a circle. Some sort of a force must be causing it to go in a circle, otherwise it would go in a straight line, and that's called the centripetal force. Okay, so we have centripetal acceleration, we have centripetal force, we have velocity, we have so much going on. Here are a couple of formulas. This one is on the AP sheet. And even though it's on the AP sheet, I have to say right now, today, it's not going to be very helpful to us, except when we move over to centripetal force. But this is the equation for centripetal acceleration, where v is your linear speed. That means how fast it'd be going in a straight line. And then r is the radius of the orbit of whatever it's moving around. Okay, but what we're mostly interested in today is centripetal force. And centripetal force is all of this. Let me talk about this. We know that F equals ma. Okay, F equals ma, but we're talking about centripetal, so I have F sub c equals ma sub c. And the centripetal acceleration formula is v squared over r. And so where I did have the a, I can plug in v squared over r. And so now I have that centripetal force is equal to mv squared over r. This is not on your formula sheet, but I would recommend you memorize this. This is a formula that we will use a lot, and if you have it memorized, that's going to help you out quite a bit. Okay, then we have a couple of terms, period and frequency, and from your study of trigonometry, you should have learned a little bit about period and frequency. The period is how much time it takes to go one complete revolution. So back to our circle. If we have some kind of object that's going around and around and around and around and around and around and around, well, great, but how long does it take to go around one time? That is the period. And it is measured in time, in seconds. The frequency is how many revolutions per unit of time. So it's revolutions per second. So depending on what it is you're moving, it might be going super fast, and maybe it goes 33 revolutions per second. Or maybe it's going really, 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 really slow, and it's only going, I don't know, 1 revolution per second, or a half a revolution per second. Okay, let's take a look at some problems to kind of help us make sense of this. Consider an object that requires 0.2 seconds to make one complete circle. Assume that this object is undergoing uniform circular motion. How many revolutions will it make in 1 second? Well, think about it. If it takes 0.2 seconds to go around once, then how many times is it going to go around in 1 second? Hopefully you can see that that's 5 revolutions per second, because 5 times 0.2 would give us 1. And so that's 5 revolutions per second. This next question, question B, is really the same question. I might have said, instead of saying RPS, maybe I just said 5 revolutions. And then this is saying what is the frequency in revolutions per second, and that will be 5 revolutions per second. Okay, mathematically, the frequency and the period are inverses of each other. It's 1 over f, or t is 1 over f, or f is 1 over t. On your calculator, there is a little button that is a -1 button, and that also will give you the 1 over. That means inverse, and these are inverses of each other. So that's another way to do it on your calculator, is with this button. And then they say illustrate this inverse using numbers from this problem. What we found over here was the frequency, that the frequency is 5 revolutions per second. But we had that the time, or the period, is 0.2 seconds. If we go into our calculator and we take 1 over 5, what does that equal? Well, it equals 0.2. Likewise, if we go into our calculator and take 1 over 0.2, what does that equal? It equals 5. Notice also that our units are also inverses of each other. So like revolutions per second, but this one is seconds per revolution. So those are flipped as well. The speed of an object in circular motion can be determined by dividing the distance traveled, that's the circumference, by the time required for one revolution, the period. We know, for instance, that velocity is change in x over change in time. If we're talking about going in a circle, well, then our distance is our circumference, and the formula for circumference is 2 pi r. And change in time, well, when we're talking about circles, we're talking about period. Our time is our period. And so velocity is 2 pi r over t. This one is not on the AP sheet. Yes, on the AP sheet, they do have circumference equals 2 pi r. So that is on the AP sheet. Okay, let's take a look at a couple of examples just to see how this works. An object that goes around a circular track of a 2-meter radius at a constant speed once every 10 seconds. All right, so first of all, we have to figure out what these mean, these letters or numbers all stand for. So this obviously is our radius is 2 meters. If it goes once every 10 seconds, then that is the period. 10 seconds to go once around. Okay, so its speed is going to be v equals 2 pi r over t. That's this equation right here. So I can say 2 times pi. The radius, of course, is 2 meters, all over t, which is 10 seconds. If we take a minute to look at our units, this is going to come out to meters per second, so that's good. Now, when we put it into our calculator, I know in math class you would say 2 pi, but in this class, that doesn't really help us a whole lot. It'd be better to give it as a decimal. So go ahead and put this into your calculator and see what you get as a decimal. Okay, I got 1.26 meters per second. Now the next question, what is the centripetal acceleration of the object? It says in 2b, we're talking about 2a. So we do have that formula up here. I kind of skipped over it because we don't use it very often, but we do use it. Acceleration is v squared over r. So if we use that v squared over r, we just found the v. So our v squared over r, that's going to be 1.26 meters per second squared. And the radius is 2 meters. So I can go ahead and multiply that out. And I'm getting 0.79 meters per second squared. If we look at our units, meters squared, but then it cancels with another meter, so we're down to meters, and the second squared is going to be here. So that is our acceleration. It says to give them both the magnitude and direction. Okay, if it's centripetal, then it is inward. And I'm going to talk about the vectors there a little bit more in just a second. Okay, if the object has this mass, 2 kilograms, what centripetal force is required to maintain the uniform circular motion? Okay, centripetal force is the one I was saying that it's going to help you to memorize it. It's mv squared over r. So that's our centripetal force. So our mass is 2 kilograms. Our v squared, we just did it on our calculator a second ago, 1.26 squared, which if you still have it on your calculator, it is 1.5876, but there it is. divided by radius, and our radius is 2 meters. We could easily just cancel those out, but let's just go ahead and do this on our calculator, and we should be getting 1.59. And we are talking about force, and force is measured in newtons, so 1.59 newtons. And then question D, what is the frequency of the revolution? So if our period was 10 seconds, then frequency is 1 over t, and so that is 0.1 revolution per second. Okay, this next example is going really old school. Have you ever seen, I think they're even calling it a phonograph record. So just an old-fashioned record, just a vinyl. And those records had certain frequencies, and the record players moved at that given frequency. So a 33 RPM was a common frequency. So what is the frequency in revolutions per second? So if it's 33 revolutions per minute, then we can do some unit analysis here and say, okay, I need it in per second. So 1 minute is 60 seconds, and that'll give us the revolutions per second. So on my calculator, I'm just going to take 33 divided by 60, and I get 0.55 revolutions. And again, my minutes cancels revolutions per second. And I can also abbreviate that RPS, which is easier. Okay, so that's the frequency. The next question is, what is the period? Well, the period is 1 over the frequency. So that number that I got, 0.55 on my calculator, I can just hit the x to the negative 1 button, and it tells me that the period is 1.818 repeating seconds. So what that means is it takes 1.8, almost 2 seconds for it to make a trip around the entire thing. Okay, if the record has a radius of 15 centimeters, what is the velocity of a spot on the outer edge of this record? So there's, let's say, a scratch, which happened frequently. Then how fast is that spot or scratch moving? That's what we're asking. And so we can use that equation we were using at the beginning, 2 pi r over t, that's the period. That's the circumference, like distance over time. So I said I was going to go and do some vectors, and I will, because actually that word velocity, it actually does apply there, and we'll talk about that. So 2 pi r, where our radius is 15 centimeters, so we'll call that 1.15. The time, the t is the period, is 10 seconds. Sorry, I was looking at the wrong problem. 10 seconds was for the previous problem. In this problem, we have found t to be 1.82. And I can talk about that in just a second as well. And so I'm going to multiply that and divide. And I'm getting about 0.52 meters per second. All right, let's talk about a couple of those things that I was talking about with vectors. So I'm just going to start a new page and kind of draw some sketches out here. Okay, let me talk about these things with our velocity vectors. So if we have an object moving in a circle, we have a velocity vector at any given point, at any given place, that point is going to have a velocity. If it went off the track, if it was cut loose from the string it was on, whatever, it's going to fly off in a straight line. And so at any given place, at any given point, it does have a velocity. And so that's why we've been using that letter V, is it does have a velocity. The velocity here, the velocity here, the velocity here, the velocity here. Each of those velocities has the same magnitude, but they have a different direction. The direction is always tangent to the circle. So that is always going to be the direction. At these other places, it will be tangent to the circle from wherever it is. And then the acceleration, that centripetal acceleration, is always pointing towards the inside of the circle. So this is my centripetal acceleration, this is my centripetal force. It is always pointing directly to the inside of the circle. It's like a radius, and it's always perpendicular to this tangent. Okay, there are a couple more questions on the back of this worksheet, which I think you can do on your own. So I'm going to let you finish those. Your homework is to finish those couple problems there, and we will turn this in.